Okay, so we're moving on from modern atomic theory, where we learned about things like atomic orbitals, which are going to be kind of important for bonding, and now we're going to start bonding. So we're going to learn about something called electronegativity today, and that will help us determine what type of bonds form between atoms. Now, the question more fundamental to that is, well, why do atoms bond together to form compounds anyway? Well, it's all driven by energy changes. When bonds form between two atoms, a lower energy, more stable state is attained. And that is doesn't always happen, because not every atom can form a bond with another one. But if they do form bonds, it always forms a lower energy, more stable state. Now let's talk a little bit about the types of bonds. You already should remember there's two basic types. Ionic bonds, which are essentially a metal and a non-metal, or a metal and a polyatomic ion kind of thing, or covalent bonds, which are formed between non-metals. There's another kind here, metallic bonding, but we're not going to discuss it. Now, you may remember all the way back the 4th or 5th class in September, or you may not, it's a long time ago. We did ring diagrams with electrons moving between the rings to form ionic bonds, and electrons being shared by overlapping the rings to form covalent bonds. Well, this ring model of bonding isn't completely accurate. It's just kind of used as a basic way of starting to get the idea of what's going on. But we know that electrons aren't in rings. They're in atomic orbitals, these three-dimensional spaces. So as you're going to find out, what happens for ionic bonds is that electrons are going to be moving between those three-dimensional spaces, so that you'll end up with one atom with completely filled s and p orbitals, and the other atom that will look sort of like the electron configuration of they both will end up looking like electron configuration of a noble gas. They'll have completely filled s and p orbitals. For covalent bonds, they do the same thing. They also will end up with completely filled s and p orbitals, but they don't do it by electrons moving from one atom to another. Basically, half-filled s and p orbitals will overlap and share electrons, sort of like that overlapping ring model we talked about before, but you'll end up with the equivalent of completely filled s and p orbitals on each atom. Now, again, ionic bond have oppositely charged ions attracted each other to form a salt. Now, salt just means ionic compound. Here it's sodium chloride, so it's table salt. But you've got negatively charged chloride ions alternating in this structure with positively charged sodium ions. And they're held together by electrostatic attractive forces. Now, covalent bonds we're going to see come in a couple varieties. One is where the electrons are evenly shared. For instance, here's a hydrogen molecule, and you can see sort of a dot diagram showing the probability of where the electrons are. And it's a little denser in between the two positively charged nuclei. That's where the bond is. Now, if you look at basically it's hydrogen monofluoride gas, and you look at how the electrons are distributed, you're going to see that they're not evenly distributed. And we have these little weird symbols underneath. This is a delta minus. It's a Greek lowercase d. So delta minus, and a Greek lowercase d delta plus over here. The dots again are showing the electron distribution. And what you can see is, for some reason, which we'll talk about in a moment, the fluorine atom is keeping the electrons a lot closer to it, and it's not sharing, it's not playing very nicely with the hydrogen atom. So the delta minus means that the fluorine half of the molecule has a partial negative charge, where the hydrogen side of the molecule has a partial positive charge. And we're going to talk about how that happens in a moment. Now, how can we tell if electrons are stolen, which means transferred between atoms, so that's forming ionic compounds, or shared unevenly, as you'll see those are called polar covalent compounds, or shared evenly, which are just called either covalent or nonpolar covalent compounds? Well, a very famous scientist named Linus Pauling he studied bonding. He spent tons of time trying to figure out bonding. He did a bunch of other things too, but he won a Nobel Prize essentially for his contributions to bonding. And he came up with the idea of something called electronegativity. What he did is he studied electrons, how they are distributed in bonds between two atoms, just between two atoms. And he saw that some atoms will tend to keep the electrons close to them. He found out that one of them was the very best at that, that's fluorine, and he just arbitrarily assigned it a value of 4. At the very other end, some atoms are very lousy in bonds of keeping electrons close to them, and he found out that that was francium, but really it was basically cesium, because francium is very hard to work with since it's radioactive. So he was able to assign these values. And if you look at two atoms when they're forming a bond, depending on how big of a difference they have in this electronegativity value that's assigned to them, we can predict what type of bond they're going to have. So, very simple rule. We're going to use this now. Is this 100% accurate? No, but it's a pretty good rule, probably 90% accurate. So it's all based on electronegativity values. You will actually have your own little periodic table that's got an electronegativity value for every atom that you can look up when you're trying to do this kind of analysis. So for an ionic bond, difference between the two values of the atoms will be greater than 2. So if you look at sodium and you look at chlorine and salt, you will see that the electronegativity value of chlorine is something like 3.2, something like that. And the electronegativity value for sodium is down around 0.9. So the difference is greater than 2. You predict when those two atoms come together, they'll form an ionic bond. Polar covalent bonds mean the electrons are not shared evenly. So when they have a difference of 0.5 to 2, that means one of the atoms keeps the electrons in the bond closer to it. So you saw that with the hydrogen monofluoride. Fluorine actually has an electronegativity value of 4. Hydrogen has an electronegativity value of 2.2. So the difference is 1.8. And the prediction is that the electrons will be closer to the atom with the greater electronegativity value. By the way, you don't have to memorize electronegativity values or have your own little chart to look them up, but you need to know this simple rule. The third thing is nonpolar covalent bonds will have electronegativity differences less than 0.5. So look, any atom bonded to itself has a difference of 0, guaranteed to be nonpolar, like the hydrogen molecule we saw earlier. What about carbon bonded to hydrogen? Well, carbon has a value of 2.6. Hydrogen has a value of 2.2. So the difference is 0.4. So between carbon and hydrogen, the electrons in the bonds between them are generally considered to be evenly distributed. So there isn't really a positive and a negative side of that bond, okay? So when you think about this, all hydrocarbons, octane, ethane, whatever, they're only carbons and hydrogens. They are all non-polar. I want you to think about polar covalent. Let's think about oxygen. Oxygen has a value of, let me think, I think it's 3.4 on the scale, and hydrogen has a value of 2.2. So if you subtract them, you get a value that's between 0.5 and 2. And so what you'll find out is that the bonds between the oxygen and the hydrogens in water are polar, meaning that the electrons will stay closer to the oxygen since it has the bigger value than to the hydrogens. When we did stuff with solubility, I don't know if you remember, but covalent compounds would dissolve at each other where with other polar covalent compounds. Non-polar covalent compounds would dissolve with other non-polar covalent compounds, but you can't dissolve these two in each other because fundamentally they have chemically different properties. Now, 3 types of bonds. Now, here's just sort of a sketch of the electron distribution. So you can see for nonpolar covalent, the 2 dots are the nuclei. The electrons are fairly evenly distributed. That could be 2 hydrogens, it could be 2 carbons, it could be 2 oxygens, it could be a carbon and a hydrogen, or anything else that has an electronegativity difference of 0.4 or less. Polar covalent typically have one end where the electrons are closer to than the other end in the bond. And that causes it to have a partially negative charge at the end that has the higher electronegativity value, and a partial positive charge at the end that has the lower electronegativity value. And if you have a big enough difference, greater than 2, you can actually end up with electrons moving between atomic orbitals, and you'll end up with a situation where you have an ionic bond, like sodium chloride. So nonpolar covalent differences are less than 0.5. Polar covalent 0.5 to 2, ionic greater than 2. So that's what you're looking for. So here's an example. The hydrogen fluoride bond, which we already have seen. Hydrogen has a value of 2.2. Fluorine has a value of 4.0. The difference, depending on how you write it, it's either positive 1.8 or negative 1.8, but here's the thing. All values by default are considered the absolute value, so it doesn't matter the order. It's going to be a positive value of 1.8. 1.8 falls into this category, so you would predict that hydrogen and fluorine would have a polar covalent bond, and guess what? They do. Now, this simple rule of bonding isn't perfect to predict exactly what type of bond you get, but it's pretty good. Now, last thing I want to point out, and you should probably actually print this, these are the electronegativity values we are going to use for our assignments. Look at each element. You see there's a value underneath it? This is not the average atomic mass. It's an electronegativity value. See, element symbol underneath has the electronegativity. You could ignore pretty much the upper right and upper left. We won't be really dealing with them. So as you can see, fluorine has a value of 4. It is by far the most electronegative atom. If you go down here, francium is 0.7, but really francium doesn't exist because it's got a very short radioactive half-life, so there's really none of it available to study. But cesium has a 0.8, so that's pretty much our lowest value. Look where they're located. Bottom left, where we got metals, and across most of the metals, they have very low values. That's why I color-coded them just so you could see. Where in the upper right, you tend to see higher values. Now, there's a few in the middle that are a little bit higher than 2, but they're not very much higher than 2. If you look carefully, you'll see I miscolored one. Do you see? Look where gold is. It's 2.4. It's supposed to be red. So, oh well, I screwed up. So, most electronegative atom, fluorine, least electronegative atom, francium, but really cesium. What group has no electronegativity? Take a look. Do you see values underneath the noble gases? Here's why. They don't have values. In order to have a value, you have to be able to form a bond. The whole point of electronegativity, the way Linus Pauling figured this out, was by studying how electrons are organized when one atom bonds to another. Where are the electrons? Who are they closer to? Well, guess what? Noble gases have all their s and p orbitals filled. They have no half-filled orbitals, so they don't form bonds, so they have no electronegativity values.